My name is Archo. I'm from Korea University. I'm going to be the chair and also the panel discussion leader of this session. I'm going to be conducting this session in English, but there could be someone who's going to give a talk in Korean too. But of course, both ways, you all know that there will be simultaneous interpretation, so that shouldn't be a problem. What else can I say? Before I go on, I have to mention that since these talks are too short, we decided that if you have any questions after each talk, you should defer it to the panel discussions time. Okay, so no questions during the interchange, the period after between the talks, but you can ask each speaker any question you might have during the maybe beginning of the panel discussion period. Okay, so the first speaker is actually myself. So I'm going to be giving a self-introduction. As I said, my name is Archo, and can we have my, okay. And I'm from Korea University, but also I run this company called inCerebro. And the title of my talk is Design of Drug Compounds Using Quantum Machine Learning. Okay, so it is no secret that drug discovery has been hailed as one of the most important fields that might benefit by quantum computing. And as you can see, there are numerous articles out there that talk about this fact. Now the thing is, if you think about why that is so, you probably have to go all the way back to the original idea of quantum computing. And the first person who ever talked about quantum computing was, you probably know, that's Richard Feynman, who is one of the greatest physicists of all time. And in his mind, what he was envisioning was a computer with quantum mechanically behaving components to simulate quantum mechanical phenomena. Well, drugs are molecules. It's tiny little things, and they are governed by the quantum mechanical physics. So people would probably think that the drug discovery would benefit from the quantum computing immensely, and also the fact that drug discovery is about business. So it involves a lot of money, and therefore it will be the first field that will be benefiting from quantum computing. Now, this is what we call a drug discovery pipeline. I just wanted to give you an idea what we do in drug discovery. There are other ways to do these things, but the first thing that we have to do is to find the target, which are usually proteins, and find the drug molecules that will bind to these proteins. Okay? So that process is called screening, and during this thing, what we'll do is to go through what we call a library of compounds. There will be like maybe millions or even billions of different compounds that we can try out and see which one binds best to this target protein. And in fact, that particular phenomenon is called protein-ligand binding. And as you can see, these are drug molecules that will bind to the part of this protein molecule. Now, the current practice is that using molecular modeling tools on the computer, we can simulate this phenomenon and make a good prediction of how they behave. If you want to introduce quantum computing, you will have to do the following. So this is something that we've done last half a year or so, is to divide the regions where this thing happens here, like binding, into little smaller parts and identify the parts that are most important in this binding the process, and try to apply some quantum algorithms to make accurate predictions. Okay, that's all good, but the problem is the following. To achieve the better accuracy than the current methods that we are still using, that are done on the digital computer, we need at least a few thousands of physical qubits to have that much accuracy. That's because you want to get rid of all the noise, and at least you want to have a few qubits that will represent the orbitals of these molecules. And that's insurmountable task at this point. As you know, we don't have such quantum hardware yet. So you can imagine that the quantum computing at this point in time is not that helpful if you want to follow this path. So we thought about on a different angle, and thought maybe the secret is in the screening process. As I said earlier, that the screening is done with the list of compounds which we call library, and the library can contain maybe millions or even billions of different molecules. Now, it is well known that if you work with larger molecules, you get better results, okay? That's for sure. And the current practice is that there are about in the order of billions of molecules are used for the screening process. However, it is also estimated that maybe the whole chemical space of 10 to the 63rd power can be used. And that's a huge difference. So how do we complement this difference? So we've been thinking about this problem for more than 15 years, and we came up with some technology that involves molecular modeling technique and also AI. And what it is this one is called water pharmacophore. And basically, in water pharmacophore, you run molecular dynamic simulations where you can extract the information about the binding site of the proteins and come up with this model that's called a pharmacophore model. And this can be thought of as what we call a blueprint for the drug molecules for a given target proteins. And using this model, you could quickly like screen out these molecules that will be later used for further processing. And what we do in this particular algorithm is you're gonna use this list of molecules to train the deep learning, which is a form of machine learning, as you all know, and let these established deep learning model to produce some new molecules. So these new molecules will be not in the library, so you're basically exploring this further into the vast chemical space, and you can go on indefinitely. So you can tap into this vast chemical space by this method. So now we thought about this in both ways. And one was using the variational quantum eigensolver and its variations to calculate the protein-ligand interaction energy. And the other one is using the quantum machine learning to generate the virtual ligand library. And we chose this as something that's practical at this point, because we could use maybe 4 qubits, as little as 4 qubits, and still get improvements over the classical method. And we came up with this protocol, which I call WPDL with QML. And through that, basically we substitute the deep learning part with the quantum machine learning and try to generate these target-specific chemical library. And we have planned, and this is part of our the project that we're doing for the grant, the government grant that we recently won. And we're going to do experimental verification at the end of it. Now, before actually applying for this government grant, we even did some pilot tests of this idea and had this following results. And we did this with using the quantum simulator. So this is going to be noiseless quantum computer model, and using the target called PARP. PARP is an anti-cancer drug target, and we got the following result. And lo and behold, the quantum machine learning was able to generate these the compounds that are more has more binding affinity than the classical machine learning. And we verify that using a docking technique, which is a molecular modeling technique to computationally determine the binding affinity. And now also the quantum machine learning it actually produced the compounds that have more like the training set. That's meaning it's more focused, so you're actually delving into deeper into this chemical space for the given question. So it's better in this way than our classical counterpart. So, yeah, I got 20 seconds now. As a summary, we tried out the quantum-based protein ligand binding affinity calculation, which shows a little bit of promise for the future, but the current state of the quantum hardware, we cannot really make it happen. However, with the quantum machine learning, even with the small number of qubits, we were able to show some improvements. So we're going to actually carry out this research in this way to realize quantum advantage in the drug discovery, which is experimentally validated. So that's all I have to say. And as I said, I'm 1 minute over, so I'm going to stop right here, and we're going to go on to the next speaker. Thanks very much.